This video is about finding the vertical and horizontal components of vectors. As we've mentioned before, a vector is something with a magnitude and a direction. In this case, the direction is going to be indicated by the angle that the force is measured to, and the vector itself will be representing a force. So the first thing we need to do is draw the vector to scale. So we choose an origin and make an X there. Then we draw our axes, a horizontal axis along the horizontal grid line, and a vertical axis along the vertical grid line. Then we choose a scale. Since we want our 20 Newton force to fit on this grid space, we need to choose a scale that will allow it to fit. So, the scale that I choose is 1 centimeter equals 4 newtons. That should work well for this one. So I go down to the conversion area and write down my scale. 1 centimeter equals 4 newtons. Now in order to find out how long this needs to be, I'm going to use FLM. We start with a force of 20 newtons because that's what the problem gave us. We're going to convert it over to centimeters. Remember, we put two things that are equal on top and bottom. So 4 newtons on bottom and 1 centimeter on top. The newtons cancel out, and I get 5 centimeters, which is how long my vector needs to be drawn. Then I go back up to the top part. Now I'm drawing a representation of a 20 Newton force at 30 degrees from the horizontal. Remember that an angle is always between two lines, in this case between the horizontal line and the force that we're trying to draw. Keep that in mind as we're doing the drawing. We know that it needs to be 5 centimeters long and at a 30-degree angle. So I have to start using my protractor. I take the center part of the protractor and line it up with the origin that I made before, the X. Then I have to slide the protractor around so it's lined up with my grid lines. I want this black line on the protractor to be lined up with the horizontal axis that I drew before. Once that's lined up, I go in and make a marking at 30 degrees. I look at the markings here, I go up to where it says 30 degrees, and I just make a little mark right there. Then I can take my protractor out and line up the inside of the protractor where I have my centimeter markings, so that the 0 is down here on the origin, and it makes a straight line with the mark that I just made. Now my vector only needs to be 5 centimeters long, so I'm not going to go all the way up to the marking, I'm just going to go up to the 5 centimeter mark. Now I've drawn this force vector to scale over here on my grid. We know that it's 20 newtons long. Now in order to find the vertical and horizontal components, I'm going to use a little bit of geometry. First I'll just draw in the two components. The vertical component is here, and the horizontal component is down here. You'll notice that these make a right angle to each other, so now we have a right triangle. If this is my 30-degree angle down here, then this is what we would call the opposite side. This is the adjacent, because it's right next to the angle, whereas this one is opposite the angle, and this is our hypotenuse. Now you'll need to remember some relationships from geometry. If you haven't learned them yet, you will be seeing them soon, so go ahead and commit this to memory. So there's an abbreviation, SOHCAHTOA, to help us remember how the sides of a triangle are related to each other. For any right triangle, we can use this relationship. Remember that we need to have the opposite side, if this is our angle here, the hypotenuse, or the adjacent side. SOHCAHTOA tells us that sine of the interior angle, let's call it theta, sine of theta equals opposite over hypotenuse. Cosine of theta, the angle inside, is adjacent over hypotenuse. And tangent of theta is opposite over adjacent. So recall that for our triangle, we had a 20 Newton force, a 30-degree angle, and we wanted to find the opposite side and the adjacent side. First relationship we're going to use is sine. As we just said, sine of the angle is going to equal opposite over hypotenuse, and we know the angle and we know the hypotenuse, so we'll be able to solve for the opposite side. The angle is 30 degrees, And if you're entering this into your calculator, make sure that you're set to the degree mode. Opposite is what we don't know, and the hypotenuse is the length of our vector, 20 newtons. So 20 times sine 30 equals the opposite. We can plug that into Google to get a calculation. So 20 times sine of 30 degrees, and you have to write the degrees so that it knows what units you're using. And opposite equals 10 newtons. Now we can do the same thing to find the adjacent. Or if you want to, you could use the Pythagorean theorem at this point. So cosine of theta equals adjacent over hypotenuse. We know that our angle is 30 degrees. Adjacent is the unknown, and the hypotenuse is still 20 newtons. So 20 times cosine of 30 equals the adjacent. Again, you can plug that in. And we get that the adjacent side is 17.32. Lastly, I'm just going to plug those values back up here as the horizontal and vertical components. We said that the opposite was 10 newtons. We can see that that represents the vertical component of our vector. The adjacent was 17.32 newtons, and that represents the horizontal component of our vector. Now we're ready to go on to the next problem. In this one we have a 65-degree angle. The difference is our vector points to the left. So we can draw the vector to scale just like before. Make an origin. Draw your two axes. Choose a scale. In this case, I choose a scale of 1 centimeter equals 5 newtons. 12 Newton force becomes 2.4 centimeters long. I draw that at 65 degrees. First putting my protractor down. Finding the 65-degree mark. Putting the 0 down here. And then making it 2.4 centimeters long. Next I'm going to be finding the vertical and horizontal components, so I'll go ahead and draw those in. Since my angle down here is 65, then this is going to be my opposite side, and this is going to be the adjacent. The total length of the hypotenuse, or the vector itself, is 12 newtons. Now I use my trig. Now I go down to the bottom to figure out the two components. Remember, we have a 12 Newton force. The opposite side is over here, adjacent is here, for the angle here, which is 65 degrees. We remember that sine theta equals opposite over hypotenuse. We know theta and we know the hypotenuse. So sine of 65 degrees equals opposite over 12 newtons. So the opposite equals 12 times sine of 65. Again, we can plug that right in. And we get 10.88 newtons. On the other side, we're going to use cosine, adjacent over hypotenuse. So cosine of 65 degrees equals adjacent over 12 newtons. And adjacent equals 12 times cosine of 65 degrees. We'll get 5.07 newtons. We go back up to the top. We calculated that the opposite side was 10.88 newtons. We can see that that's the vertical component and it points up. So we write that in here, 10.88 newtons. We calculated that the adjacent side was 5.07 newton, but we see that the vector points to the left. Since in our axis over here, to the left is on the negative side, then anything that points in that direction, we're going to let it be negative. So instead of writing positive 5.07, we write negative 5.07 newtons. Now we're ready to go on to the next one. Here we have a vector that's 15 newtons long, but the measurement of 75 degrees is measured from the vertical rather than from the horizontal. Remember that an angle is always between two lines. In the previous two examples, it was between the horizontal axis and the vector that we were drawing. In this case, it's between the vertical axis and the vector that we're drawing. We're going to have to keep that in mind when we draw it. Here I choose a scale of 1 centimeter equals 3 newtons, which means that my vector needs to be 5 centimeters long. I choose a starting point, draw my axes, find the 75 degrees. Now, in order to find a 75 degree angle from the vertical, I need to turn my protractor so that it's lined up with the vertical axis. I still put the circle right at the origin, and I swing it back and forth until this black line here is lined up with the vertical axis. Now I look for 75 degrees in my degree markings, which is down here, and I can turn it and draw my vector. Again, I'm going to make it 5 centimeters long. I line up the 0 with my origin, turn the protractor until it's lined up with the marking that I just made, and draw a vector that's 5 centimeters long. 15, which represents 15 newtons. Now again, I'm going to be finding the vertical and horizontal components, the vertical component being here, and the horizontal component being here. But we said that the 75 degrees was measured from up here. Well, it turns out that we can find the vertical and horizontal components from that side as well. So in this case, the vertical component will be, well, the horizontal component will be here, and the vertical component is here. Since our angle is here, we made a right triangle that looks like this. I'm just going to redraw it over here so we can see it clearly. The inside angle is 75 degrees, and the hypotenuse is 15 newtons. We're going to be looking for the opposite, which is now up here, and the adjacent. So again, we have a 75 degree angle with a 15 newton hypotenuse, and we're looking for the opposite side and the adjacent side. First we can use sine. Sine theta equals opposite over hypotenuse, and plug in what we know. The angle is 75 degrees, the opposite side is unknown, and the hypotenuse is 15 newtons. So the opposite side is 15 times sine of 75 degrees. We can plug that in. And we get 14.49 newtons. On this side, I'm going to use cosine, adjacent over hypotenuse. Our angle is 75 degrees, adjacent is unknown, and hypotenuse is 15 newtons. So adjacent equals 15 times cosine of 75 degrees. And that comes out to 3.88 newtons. Be careful when you take those values and plug them back in up here. Remember that the opposite we calculated was 14.49, but this time the opposite represents the horizontal component of the vector, not the vertical component. So opposite 14.49 goes here, and it's positive because we point to the right. The adjacent was 3.88. We can see that that's the vertical component, and it's also positive because our vector points upwards.